Hello, everyone. Thanks for coming. My name is Michael Kearns. The title of my talk is The Ethical Algorithm. I am a scholar here at Amazon working in AWS on AI ML problems. And as a scholar, I also have a faculty position in computer science at the University of Pennsylvania. The title of my talk is actually also the title of a book I recently wrote with a good friend and colleague, both at Penn and Amazon, named Aaron Roth. He is also an Amazon scholar. And our book, The Ethical Algorithm, in many ways is a reaction to other recent mainstream general audience books on what we might think of as the collisions between technology and society, particularly around AI and machine learning. And just to be clear, the books that we're showing here, some of you may have read some of them, notably Weapons of Math Destruction and Algorithms of Oppression, are relatively recent books about the potential for bias and other harms in AI and machine learning. My co-author Aaron and I, we admire these books very much and think that they play a very important role in bringing to society's attention the fact that even though technologies like AI and machine learning have yielded tremendous societal benefits in the last decade, there are also side effects that can come from them that are sometimes harmful. And so why did we write another book on this topic? Well, what we thought was missing from the prevailing literature was a description of a recent scientific agenda that's been underway for maybe 5 or 10 years now, that rather than seeking regulatory or legal solutions to these types of collisions, which we also think can be important in some circumstances, actually consider scientific or technical solutions. And the way I might put it kind of very simply is that AI and machine learning, after all, are human-designed technological artifacts. They are algorithms for the most part. And if there's something that we don't like about the behavior of our algorithms, we should think about fixing those algorithms in the first place, maybe changing the way we do things, the way we design algorithms and models in order to avoid some of these problems. And that's really the scientific agenda that our book describes. So what I want to do today is just give a whirlwind taste of what this agenda looks like. It's a very fast-moving field. It's a very exciting field to be doing research in. But just so we're all on the same page up front, this agenda is really about embedding social values in algorithms. And so what I mean is literally in your Python code, having lines that enforce different kinds of social norms, if you like. Things that many of you have probably thought about or are familiar with, things like privacy or fairness, accountability, interpretability, explainability, and the like. And one of the things that's interesting and different about this agenda, after all, people like me are far from the first to have thought deeply about, topics like fairness, which goes back to at least the ancient Greek philosophers. One thing that's different about this recent agenda is that when you're going to actually embed lines in your Python code that enforce social norms, you need to be exceedingly precise about definitions. You need to say very precisely what exactly you mean by something like privacy in machine learning or fairness in AI. And it turns out that sometimes being that precise about definitions has benefits all by itself, even though it's a prerequisite to this agenda. It sometimes causes you to see flaws in your intuitions about these topics that you weren't going to discover any other way. And I'm going to try to illustrate that in the brief time that we have here today. And so what I want to spend my time today doing is just giving you a flavor of what this research agenda looks like and kind of where we are with it in just the two areas that have probably been studied the most to date. One is privacy and the other is fairness. And if there are kind of two high-level messages I hope you take away from this, aside from just the fact that people are working on this stuff from a scientific perspective, it's that, first of all, enforcing social norms is important, but will also inevitably come at a cost. So in particular, in the case of machine learning specifically, it turns out that if you want to demand privacy of some kind or fairness of some kind, that might need to come at some cost to predictive accuracy. And so the way we think about this as scientists is understanding those tensions and trying to quantify those trade-offs so that we can make informed choices about the right balance between things like privacy and fairness and accuracy. And the other takeaway message is that it's not enough just to be precise. It's possible to be precise about definitions and to get it wrong. And I'm going to give a couple of examples of cases where we feel like there are precise definitions that have gotten things wrong. And then, of course, I'm going to tell you about what I think better alternatives to those definitions are. So let me start off with privacy. And let me start off with what has now largely become viewed as a discredited form of privacy in general, which is anonymization techniques, right? And anonymization techniques, of course, are not only one of the historically most prevalent set of techniques for data privacy, they are also baked into many of our laws and regulations, like the demand to remove personally identifiable information in healthcare law as encoded by HIPAA in the United States. And so what's the idea of anonymization? The idea of anonymization is that I go to a data set and I might delete entire columns because I think that they're personally identifying or sensitive in some ways. So here, for instance, at the top, I'm showing you kind of a toy medical database in which names have been redacted entirely. The last 2 digits of zip code have been redacted. Gender has been preserved. Age, rather than being given in exact years, has been grouped into 10-year periods. And the idea is that perhaps if I do some mixture of redaction and coarsening of the information, you wouldn't be able to identify any particular person's medical record in this allegedly anonymized data set. And so, for example, in the amount of anonymization that's been given in this particular table on the top, even if I knew that my neighbor Rebecca, who I know is female and 57 years old, has been a patient at this hospital, when I go to this anonymized data set and I look at the rows that match what I know about my neighbor, which are the 2 that are highlighted in red, I'm confused about what her actual diagnosis is because it could either be HIV or it could be colitis. Now, my neighbor might already think that that's a violation of privacy, but you might imagine if we did enough of this that 100 records matched what I knew about my neighbor, then I really wouldn't know much about her diagnosis. The real problem with anonymization techniques comes from what are sometimes called linkage or triangulation attacks. So on the bottom, I'm showing you an anonymized data set from a different hospital, and I might also know that my neighbor has been a patient there. And in this bottom data set, there are 3 rows matching what I know about my neighbor. The problem is when I take the join or the intersection of these 2 data sets, I now unambiguously know that my neighbor has been diagnosed as having HIV, because that is the only diagnosis that falls at the intersection of the red records of the top and the bottom. Okay, so of course, this is a toy example designed to show what the problems might be. And I think it's fair to say that the first decade of this century were spent in a whack-a-mole game between defenders of anonymization techniques and their critics, in which problems like this would be pointed out, and anonymization defenders would say, well, here's a fix for that problem. And then the critics would say, well, here's what breaks that solution, et cetera. And I think it's roughly around 2010 that this game of whack-a-mole ended, with people really realizing that these techniques kind of couldn't be saved, that they really didn't offer any formal privacy guarantees to the individual. And kind of the death knell was this 70-page law review article that came out in 2010 called Broken Promises of Privacy, responding to the surprising failure of anonymization, that really kind of documented all of the problems that have been found with this set of techniques. So if I'm telling you that anonymization is a precise but broken ideology or definition for privacy, what's a better one? Well, starting at about 2005 and gaining quite a bit of momentum in recent years is an alternative definition or notion of privacy that's called differential privacy. And then the idea behind differential privacy, I'm not going to try to give the technical definition because it's a bit mathematical for a talk like this. But the high level idea of differential privacy is we consider a thought experiment. So imagine that we have a database of medical records and one of them is yours. It's the one highlighted in red. And maybe you're concerned about your medical record being fed to my algorithm, which for instance might be training a neural network to predict the probability that somebody has a rare disease, a model that we really might as a society find valuable, okay? But you're worried that your medical record being used in this machine learning experiment might leak sensitive information about your medical record. So in differential privacy, we consider what this algorithm is going to do, and we say, look, let's consider running this algorithm with all of the medical records as input, and let's consider running the same algorithm with all of the medical records except yours, which is removed. And what we ask in differential privacy is that the output of this algorithm be controllably close under those two cases, that the output distribution, if you like, of the algorithm be negligibly different, whether your data was or was not included. And if you want an intuitive description of why this is a good definition, one of the consequences or implications of differential privacy is that a third party looking only at the output of the algorithm cannot distinguish much better than random guessing whether your medical record was in the input or not in the input. And if a third party can't even tell if your data was used or not, they certainly can't tell anything specific about your data itself. This is the idea behind differential privacy, and the way one achieves differential privacy is by adding noise or randomization deliberately to computations in a way that allows aggregate facts to be extracted from the data, things like correlations or machine learning for that matter, while protecting very strongly data privacy at the individual level, at the row level, if you like, in a database. Let me just quickly demystify this by describing the first known instance of a differentially private algorithm or protocol, which amusingly predates the definition of differential privacy by 40 years. It's a technique from social psychology known as randomized response. It's a protocol designed to elicit truthful aggregate responses to a question that might have an embarrassing or stigmatizing answer. So suppose I wanted to, survey a large population on the question, have you deliberately violated social distancing guidelines during COVID? So if I try to conduct this survey in the obvious way, just going up to people on the street and asking them this question, we might expect a massive underreporting of the yes answer because people might feel embarrassed to say that they had deliberately violated social distancing guidelines. So here's what you do in randomized response instead. And you can see now you'll see where the noise plays a role here. I basically ask you in the privacy of your own home to flip a fair coin, okay? And if the coin comes up heads, which is the top branch of this little tree, then I ask you to answer truthfully. Have you violated social distancing guidelines, yes or no? If, on the other hand, the coin comes up tails, which happens with probability a half on this bottom branch, then I ask you to flip the coin again and just use the outcome of the coin to answer. So in the second coin flip, if the coin comes up heads, you answer yes, regardless of whether you've actually violated social distancing guidelines or not. And if it comes up tails, you answer no. So I hope that all of you can see that there's a very strong notion of privacy here that is provided to you if you follow this protocol. And I might call that notion of privacy plausible deniability. Because absolutely anyone who answers yes to this protocol, if I confront them and I say, you violated social distancing guidelines, they can say, of course I didn't. But the first coin came up tails and the second coin came up heads. And so I did what you told me to do and I answered yes. And everybody can simultaneously give this plausible deniability. But a little bit of arithmetic reveals that if everybody follows this protocol and it's a large enough population, then we can back out a very accurate estimate to the true aggregate fraction of the population that's violated social distancing guidelines. And this is exactly what differential privacy tries to do. It tries to preserve statistical correlations at the population level while preserving individual privacy in a very strong way. So in recent years, differential privacy has gotten quite a bit of wide-scale deployment in the tech industry and elsewhere. Notably, early last year, during the start of the pandemic, Google started publishing weekly community mobility reports that would tell you in large metropolitan areas where there were large numbers of people gathering for uncomfortably long periods of time. So you might want to avoid going there or stop being one of those people. And they did this, of course, from the geolocation data on Android devices. And they know, of course, that this is highly sensitive private information. So they released these kind of mobility heat maps under differential privacy. They added noise to the data in a way that preserves differential privacy. The real moonshot for differential privacy is actually underway even as we speak, or is starting to be rolled out right now. Every statistic and report released by the 2020 US Census is going to be released in a differentially private fashion. So noise is going to be added to, county level and more granular counts that are released by the US Census. And this is not without costs, as I mentioned, because as you can imagine, adding noise to data or computations reduces its resolution or accuracy. And so here's the front page of a New York Times magazine op-ed, basically pointing out that certain very small communities might be entirely disappeared by the noise added by differential privacy. And of course, this could have real consequences in cases where federal budgeting decisions use the counts released by the census, okay? But there's no kind of scientific way of avoiding the fact that the more privacy you want to provide to individuals, the less resolution or accuracy you can provide in the results of your computation. The important thing to do is to understand quantitatively what those trade-offs look like so that we can make informed choices about them. And that's a great deal of what the research in this area looks like. Let me just now spend a little bit of time talking about fairness, and fairness in machine learning in particular. Compared to differential privacy, this is a much less mature field. There's not widespread agreement on the definitions, and we're only just beginning to understand what the trade-offs look like, not just between fairness and accuracy, but different types of fairness. But what I want to do is just spend my kind of last few minutes here just showing you how machine learning might be unfair in the first place without there necessarily needing to be any malfeasance by any human actor or engineer or scientist who is training and deploying machine learning models. So imagine that we were asked by some college admissions office to help them build a predictive model for success at that college, based on just two variables from a high school applicant's application. So on the x-axis, we're going to measure high school grade point average. And on the y-axis, we're going to measure SAT score. So each of these yellow points has an x value that represents the high school grade point average of the applicant to the college, and the y value is the SAT score. And the pluses and minuses here indicate whether that student actually succeeded at that college. This is historical training data, okay? And so the pluses mean that that particular student met the criteria for success, and the minus means they didn't. And for the criteria of success, let's just pick any objectively measurable outcome, like graduating within 5 years of arriving at the college with at least a 3.0 GPA in college, okay? And so notice here that I'm showing you data not just of applicants and not just of students that were admitted, but that actually came to the college, so that I know what the outcome for that particular student was. And so this cloud of points kind of looks like what you might expect. The pluses, the successful students, tend to be up and to the right, higher GPAs and higher SAT scores. The minuses tend to be down and to the left, but there's noise, right? There's some minuses that are rather high up, and there's some pluses that are rather down low, okay? Now, even if you didn't know anything about machine learning, which is probably not too many people in this audience, if I asked you to eyeball this data and build a predictive model, you very might well choose this linear separator. You might draw this red line through the data and say, like, well, based on the historical data, I'm going to predict that any point that falls above this red line is going to succeed, and any point that falls below it is going to fail. Okay, and you can see that this does a imperfect but pretty good job of separating pluses from minuses. There's some minuses well above the line, students that would have succeeded, students that actually didn't succeed, that this model would have accepted. And there are some false rejections, like this point far down at the lower left, that this model would have rejected that actually succeeded, okay? But this is actually the linear separator that minimizes the error on this historical data. Now, suppose I told you, though, that this wasn't the entire population, this wasn't the entire historical training set. There's another subpopulation, the blue points, and here they are. And there's a few things to observe about the blue points. First of all, they are a minority population in the literal sense that there are far fewer blue points than there were yellow points. Secondly, there seems to be something systematically different about the blue points. Their SAT scores seem lower. The blue cloud seems shifted down on the y-axis compared to the yellow points. And I might offer the following narrative to explain that. Perhaps the yellow points were from a wealthier demographic, and being from a wealthier demographic, they had both the time and money to pay for SAT preparation courses and tutors and multiple retakes of the exam, all of which take time and money. Whereas the blue points, the blue students can't afford that, right? They just do a bit of self-study, they take the exam once, and they take what they get, okay? But despite that, it is not the case that the blue students are less well prepared for collegiate success than the yellow ones. If you had counted carefully in the yellows, you would have seen that slightly less than half of them were pluses, whereas in the blues, it's exactly 50-50. And of course, if I asked you to build a predictive model for the blue population alone, you would probably pick this purple line, which does a perfect job of separating pluses from minuses. So what's the problem here? The problem here is that when I look at the combined cloud of points and I say, what is the model which minimizes the overall training error on this combined cloud of points, it is unfortunately exactly the same model that we would have chosen on the yellows alone. And it's easy to see why visually. If we try to move this red line down far enough to actually pick up and accept the 5 blue pluses, we will pick up so many more yellow minuses along the way that our overall error will go up. And so now we see why machine learning in its original form can result in bias, right? Because the model here that minimizes the overall training error, the red line, is now quantitatively unfair in a specific way. If we think of false rejection as the greater harm, the type of mistake that's the greatest harm to an individual, this model has a false rejection rate on the yellow population that is close to 0, and it has a false rejection rate of 100% on the blue population. Now, you might say to me, well, this is silly. Why don't I just build a 2-part model? If you're from the yellow population, I'm going to apply the red model. And if you're from the blue population, I'll apply the purple one. And now I would have a false rejection rate close to 0 on both populations, and my error would be lower. Unfortunately, to the extent that we have laws in the United States, at least, that try to get in a precise way about fairness, this kind of model may be illegal. Because if, for example, yellow and blue are actually racial groups, for example, in the United States, since the 1970s, it has been against the law to design a consumer lending model that takes race as an input. What I'm showing you here is an example where insisting that we exclude race as an input to the model, combined with the standard way of training a machine learning model, will actually result in harm to the very group that we thought we were protecting by excluding race as an input, okay? So what's a better thing to do? Well, a better thing to do is to actually change the way we train models. And instead of asking for the model that simply minimizes the training error, period, let's solve a variant of that problem. Let's basically say, let's find the linear separator that minimizes the training error, subject to the constraint that the false rejection rate between these two groups is at most, let's say, X%. And now this X% is a knob that I have. If I set X to 0%, then I'm demanding absolute equality of the false rejection rates between the two populations. If I let it be 5 or 10%, I have a more relaxed problem or constraint. And this leads, of course, to a trade-off between the amount of fairness that I'm getting, the amount of accuracy that I'm getting, right? Because, of course, if I let this knob go all the way to 100%, then basically I have no fairness constraint whatsoever. And on real data sets, you can actually plot out the trade-off, the efficient frontier, if you like, that we face between accuracy or error on the one hand and fairness on the other. And that's what these plots are actually showing. On real data sets, think of each red point here as being a different model. In this, let's look at the left-hand panel. And on the x-axis, we're measuring error, overall error population-wide. And on the y-axis, we're measuring unfairness, like the difference in the false rejection rates between two groups. And so you can see, the two extremal points are the ones that minimize, the point at the top, the upper left of the curve on the left-hand side is the point that minimizes the error at the expense of the highest unfairness. And the point at the far right is the point that has the smallest unfairness at the expense of the greatest error. And in between, we get some shape that might vary from data set to data set. And I posit that this kind of curve is what stakeholders in these different domains, like college admissions, should be looking at in thinking about if and how they use machine learning in their admissions process, for example. Okay, that's all I had to say. I hope that this gave you some flavor of what is, I think, a very exciting and important research field that there's a large number of us at AWS and elsewhere at Amazon that are very actively working and thinking about these areas. And I've given my contact information there for anybody who wants to reach out to me offline. Thanks for your attention.